Good afternoon, everybody, and thank you to McEwen for this invitation to come and speak with you. And I'm going to be talking about what some might refer to as a disruptive technology, because what we've attempted to do is make a change to the mechanical aspects of froth flotation in a fairly dramatic way, and I'll talk about that in a few minutes. I'm the Vice President of Woodgrove Technologies. We're based here in Toronto. Flotation has been the core to my career for 35 or 40 years now. I met Nate first at McGill. I ended up doing about 11 years at that institution and came away with a few degrees, and I taught at U of T for a while. I was working for Inco for a while, and then I was one of the lead staff at Minivex Technologies, and we sold Minivex in 2005. My business partner and I, Glenn Kozak, started Woodgrove the fall of 2009. So what I'm going to talk to you today is where we stand with this technology, but most importantly, I want to talk on the theme that Nathan is interested in, and that's how to integrate technology, how to bring technology that a smaller company has developed into the mining industry. And you mentioned the article in the Globe and Mail this weekend. Well, this gentleman is the CEO of Dundee Precious Metals, and that's his plant right there in Chelopech. And Dundee is one of the companies that I'll be speaking about as a company that's helped us through their approach to integrate this technology. So our objective has been to dramatically reduce both capital cost and operating cost of froth flotation circuits. And by dramatic, what we want to do, at least for the roughing aspect, we're interested and we think we can do, and we believe we've proved it, a 50% reduction in footprint and a 50% reduction in power consumption. So as you can imagine, the impact on capital costs and operating costs for big copper plants, for example, is pretty significant. This is one of the devices I'm going to show you. This is our flotation cell operating at Salobo in northern Brazil. I'll be talking about that in quite a bit more detail. And that cell, when the project was finished, was moved to Salobo, which is the sister plant, if you wish, of Salobo in the Carajás region. And we've just finished supplying 4 new vessels for them, and that's a view of the froth treating rougher tailings. The tailings they were throwing away, this is a unit producing froth off of that. So Nathan wanted to know a bit more about froth flotation, so we're going to have froth flotation 101. Froth flotation has actually been around for, as Nathan said, more than 100 years, but it's incredibly complex. I think it's one of the most complex industrial processes that there are, because it involves chemistry that's scary complex, hard to understand sometimes, various aspects of physics, and of course a highly varying feedstock to the plant. So I want to give a quick review on flotation and use that to show where we felt there was an opportunity to improve. And I'll talk about the technology that we developed, and then most importantly I'll talk about the approach to integrating this technology, and finally give a bit more about who we are. So I'm going to keep this simple. Let's consider an ore body that has 3 mineral species. So we're trying to recover copper. So you've got copper sulfide minerals. Almost always you have pyrite getting in the way, and then you have everything else. We'll call it rock, silicates, carbonates, oxides. So 2 broad aspects. There's the chemistry in flotation, and you can think of the chemistry broken down into 3 primary categories. Surfactants, to create a hydrophobic surface on the copper sulfides. We refer to those as collectors. It's not uncommon today to have 2 collectors in a flotation circuit. It used to be we just had 1, but the chemical suppliers have been able to fine-tune that. And we have surfactants to generate small gas bubbles and ensure that we get a proper stable froth with these bubbles that have collected the particles. These are frothers, and again, it's pretty common now to have 2 frothers in a plant. Then we have various modifiers to control pH. So that's the chemistry aspect of the course. That's finished. We're going to move on to the physics of the course, and that's what I'm going to focus on. The physics is pretty straightforward. Number one, you want to create an opportunity for bubble particle contact. So these particles, some of them have been selectively made hydrophobic and others are not. So now you need to bring them in contact with a gas bubble. Then you need to create an opportunity for froth collection in a relatively quiescent environment. We're going to be talking about this, create an opportunity for bubble particle contact. So how do we do that in industry? And there's a few different ways. The simplest one is column flotation. This is a photograph of flotation columns at Cerro Verde in Peru, 5 meters in diameter, 14 meters tall. There's 4 of them for final copper cleaning. Generate gas bubbles at the bottom by sparging air. Bubbles rise up and contact the slurry that has the particle. So it's just called coursing bubble flotation. Another approach, very different, is feed slurry gas contacting devices. There's various of these in the industry, Jameson pneumatic contact cells. And with these, you bring the slurry in contact with air under pressure, so the slurry is pumped typically, and you have a very rapid process. So the residence time in flotation columns is 30 minutes, sometimes much more. The residence time in the contacting part of this device is less than a second. So 2 dramatically different ways of collecting gas bubbles. But these guys aren't the workhorse of the flotation industry. This is mechanical cells. This is a shot from the Laguna Seca concentrator at Escondida, BHP's operation. These are 150 cubic meter tank cells. Copper plants today are routinely putting 300 cubic meter tank cells in, and many projects are now looking at 500 and 600 cubic meter tank cells. They're just getting bigger and bigger. So if you look at the schematic here inside the cell, there's an agitator, and we're obviously creating gas bubbles at the agitator. So we ask ourselves a question: which mechanism of those 2 mechanisms that I described, coursing bubble or high shear, really dominates the mechanical cell in flotation? Our conclusion is the majority of particle collection occurs at the impeller, in the impeller zone, at the birth of the bubble, if you wish. I like to call it the Little Bang theory instead of the other one. So what this tells us is that a lot of this area in the cells, not much is happening. There's some coursing bubble particle collection, but it's really inefficient. So where the particle collection is occurring is right there. So that has provided an opportunity, we believe, to achieve significant volume savings and significant power savings. So I'm going to talk now about how we took that information and proceeded with what we call our SFR technology. So that's the end of the flotation course. I'm an easy marker. Don't worry about the tough exams at the end. Froth flotation is pretty complex, but we've tried to break it down into this aspect of the mechanics that we think we can make a change on. There's the same schematic we just saw. So what we're saying is that's the zone of importance for particle collection. And in a tank, in a cell like this, the slurry gets pumped around many times, 5, 10, 15 times, so particles come back. But the collection occurs really when they go through that impeller. So we've taken that zone and we've made a chamber. We call it the particle collection unit. It's the first unit of 3 stages that we have in our device. So the mechanism is quite similar, except instead of when it pumps around, instead of the slurry flying out into the cell, it hits the wall and comes back in. Okay, we inject air in the bottom of that. So this is the unit that we eventually built in Brazil. It runs at 930 tons per hour, which was 50% of the flow at Sossego. Feed slurry coming in, and this is that little schematic I just showed you, the particle collection unit. This is a pretty big one, obviously. Drive at the top, the agitator inside, and then what happens, we now have particles attached to gas bubbles. So now we want to recover those from the slurry. So there's a transfer pipe that carries the slurry and the gas bubbles across into the next units. We've got a bubble disengagement unit to allow slurry to come out and exit a tailings valve that you can't see, it's on the back side. And at the top, a froth recovery unit. So each of these 3 stages can be individually designed for optimizing that process. For example, the froth recovery unit, we will often constrain it to very, very small surface areas. So hence, it's a staged, there's 3 stages, it's flotation, and we needed a noun. Reactor sounded better than thing, so there we are, where it's our staged flotation reactor, the SFR. And we developed, the first one you'll see in a few minutes was run in Newfoundland. The top of the unit is much smaller surface area than mechanical cells. So we have very high solids flux off the top, and we have an extremely low gas rate, 10 to 15% of the gas rate that would be used in a mechanical cell. So it's really, so we end up with higher selectivity and obviously lower costs for gas. And again, here's the top of the unit at Salobo. Just a few more photographs, and I'm going to come back to this. This is at Chelopech, Dundee's operation. Very first one we installed was at the Pine Cove concentrator of Anaconda Mining. It's in northwestern Newfoundland. This operation has been in operation continuously 24/7 now since July of 2010. It only runs about 45 tons an hour, and one of our objectives was to take that and go to the industry, and the industry was saying, well, we need it at 1,000 tons per hour. So the issue of scaling up is where we got the assistance from industry that you will see became so critical to allowing us to do this rapidly. So the advantage of this project for my business partner, Glenn Kozak, and I was that we had an opportunity to work with some fabulous people in Newfoundland. The guys there were tremendous people to work with, and they're still running this little operation, Anaconda Mining. So a summary of our technology: the mechanical shear for bubble particle contact is not coursing bubble, and it's not pumping, so we don't need to pump into each one. The froth area is compressed. We can use froth water washing, and we have no pumping between stages. So you can see you go down like mechanical cells will. The net effect is a significantly lower footprint and a significantly lower power consumption. So I'd like to talk now about 2 approaches we had to integrating this technology. First one was what I would like to call the early adopter, and that's Dundee Precious Metals. Nate referred to Rick Howes, who's the CEO of Dundee. Rick and the other fellows there, Simon, Meek, were really critical in allowing us essentially to help develop the technology at their concentrator. They believed in what we're doing, and they were prepared to share the risk with us, and that was absolutely critical. So we started this at the Chelopech operation in Bulgaria, copper gold operation. We started with 4 SFRs for copper cleaning. We had 1, and then we installed 3 more. That replaced 26 older and smaller mechanical cells. Installation occurring of the SFRs. You can see the agitator here. So that's a small tank separate from the vessel that the froth is removed on, and a view of the froth at the top. We then went on and had the opportunity to install 8 SFRs for a new pyrite gold circuit that Dundee installed. That's now been running for 2 years, and that is this circuit here. This is an existing building they had. You can see it's long and narrow. There wasn't enough room for mechanical cells. The SFRs fit into this building. So we have 8 units producing a pyrite gold concentrate that they sell for the sulfur value and for the gold value. Another early adopter was New Gold's operation at New Afton in British Columbia, Kamloops. We did a lot of pilot plant testing on site with New Afton, And subsequent to that, we ended up installing 3 units. A paper was presented on it at the CMP in January, passed. And these guys here, now the 3 of them are producing 60% recovery off of the regrind cyclone overflow. That's 8% copper, and these take it up to 30% copper. Each of these pipes here are carrying underfroth water to allow for a increased concentrate grade. Installation occurring, and you can see here the froth zone has been necked down a lot, so I referred to that earlier, that we can manipulate the size of each of these 3 stages independently, so that is optimized for the amount of solids that want to come off, and there's a top view of it. So the second approach we had was the consortium. This consortium we put together, the objective was to demonstrate that we could scale up from 40 tons an hour to 900 or 1,000 tons per hour. These are the companies that participated in it, all of them financially, but especially Vale. Vale put up their hand and said they wanted to be the host company for the site. And that worked out exceptionally well for us. It was a long project. The project spent between $6 and $7 million. It took about 3 years to complete, and we issued the final report on it just about 8 months ago. Objective was to demonstrate scale up to approximately 930 tons per hour. And we had the opportunity at this plant to treat both rougher feed and rougher tailings. It's an outdoor plant, and the rougher feed and the rougher tailings of 50% of the plant was piped into this unit so that we could run head-to-head against the existing equipment. Sossego mine is in the Carajás region of Brazil. It's been in operation now for 11 years. You can see the flotation circuit here. There's 2 lines of rougher cells, 7 cells each, 160 cubic meter tank cells, and we took the feed of one of those rows and diverted it. The SFR was sitting in this region down there. And again, that's the unit. The project included getting this built. We looked after the construction of it in Belo Horizonte, and then there was supply of all this equipment, an awful lot of piping, a lot of engineering for this project. And here's a view of the system in operation on rougher feed, and this one is on rougher tailings, where we narrowed the opening down to get a very high solids flux at the end of the circuit. So as we progress down a bank where we have lower and lower solids coming off, then we can make the diameter at the top smaller as well. And we simulated that with this unit by being able to put inserts at the 2 sides here. Another view of the unit operating. The conclusion of the project, immediately after Vale purchased the unit and moved it to their sister plant, Salobo. Salobo started up, it's a copper gold operation, started up about 4 years ago. That was Salobo 1. Salobo 2 started up about 1.5 years ago. And they moved, and it's only about 150 kilometers apart, these two concentrators. So this is the same particle collection unit as you saw. We built a new unit here. The previous one was 5 meters in diameter. We found out that we didn't need it that big. This one's 2.9 meters diameter, and it goes up to the froth there. That started operation in August of this past year, and within a month it was working to the point that they ordered 3 more of them. There's 4 rougher rows, and this has been installed as the last stage of roughing. In other words, collecting copper and gold that was going out to tailings. So we're currently commissioning the next 3 units right now. That's the top view of that unit. Some other current projects that we have going. Krumovgrad, Dundee will eventually put a plant in Bulgaria, the Krumovgrad operation. gold operation, and we've completed the engineering on that with 19 SFRs for roughing and cleaning. BHP, we've been very active with BHP on their Spence project, which will be copper flotation circuit in northern Chile. And we've done about 300 pilot plant runs in Santiago, Chile, and we're doing more today as we speak, variability. And the engineering is underway right now for SFRs and copper roughing, copper cleaning, and for the moly circuit. So we have many pilot plant and design projects underway. This is the pilot plant. It runs, we can typically run with about 25 or 30 kilograms of drill core ground to do a test where we can then simulate multiple stages, as many stages as we want, 10 or 12 stages in a row. Take a batch of feed and run it through. So it's a pretty simple unit, and we can take it into plant sites as well. We can put several of them together in series if we need to. This is in Santiago. Generally, we work with one. And we presently have 6 of these pilot plant units scattered around the place. So who are we? Well, we're called Woodgrove Technologies. We now have about 40 staff, mostly engineers. The engineers are mostly process engineers, but also electrical and mechanical engineers. Our head office is here in Toronto. We have satellite offices in Vancouver, Santiago, Belo Horizonte, and Johannesburg, and each one of these satellite offices with really well-qualified engineers running those offices. So people who know us would say, I didn't realize you were that big. Well, we weren't that big until about 3 weeks ago when we merged with Portage Technologies. So this Michael Schaffer from Portage gave you guys a presentation November past, I think it was, on his technology, and we have brought these two companies together, friendly merger. Portage has froth characterization systems amongst other aspects that you saw. And it has cyclone detection systems. Both of these will enhance our offering to industry as we bring rougher applications of SFRs to the industry. So I think it's a really compatible group between the two companies. Finally, I'd like to thank Simon Meek in particular, Konstantin Petkov, Costa Petkov from Dundee, of course the whole Dundee organization, for the opportunity to go into Chelopech and for them to have the blind faith essentially in us to be able to go out and do the work. And our thanks to Vale and the many corporate partners in the Salobo SFR program. It was challenging, really challenging project. Of course, doing anything in the Amazon makes it more difficult, but the engineers at Vale were fantastic to work with. This is the Salobo SFR team, and those guys helped get us through all of this. So in closing, I'd just like to say that this, I think, is a pretty good example of how smaller service technology company that Canada has hundreds or thousands of, in everything from geology to mining to processing to material science. I think this is a couple of good examples on how we being the smaller companies, can integrate with the mining companies. And we obviously cannot do it without projects like this. We want to deliver things the mining companies want, otherwise why do it? And by having projects like this where we can have the collaboration, both sides are prepared to take the risk, then I think there's a lot to be gained. Helps us make some of these paradigm shifts that our industry needs and our society wants us to do. So, thanks very much for your attention, and open to any questions you have.